Okay. So some announcements before we get started. There are two surveys that are live right now. So I have just a general course survey. It's due tonight. There's some data I want to collect within that survey before the end of the semester. So I'll send out a friendly reminder email to those of you who don't have it finished today. It's meant to boost your online homework grade, especially if you don't have 100%. It can only help your homework grade. Next, there's a lab survey that was posted last week. This is due on Friday. That's when the majority of lab assignments are due for this semester. That lab survey is actually a line item in your lab grade book, so it will hurt your grade if you don't complete it. I will also send out reminder emails to complete that lab survey. VOL, Monday folks did VOL earlier this week. That was a short Zoom discussion lab, but we've finished the majority of electrochemistry, so you should be able to complete that lab. But this Wednesday starts our lab time final review session work. So that page is already posted. The Zoom rooms are already there. So yeah, in place of lab this week, you'll have those Zoom review sessions, but this session will be different. There will be no upload. All of your points just come from your on-time attendance. So there will be no upload because I want to cut off for upload assignments. So attend, you will get your points. And participate, of course, for like the 90-minute session to review for the final exam. Moving ahead, okay, we have 2 lectures left this week. We're going to finish all the lecture material on Thursday. There's just some spots in chapters 12 and 13 we have to finish up, and then whatever time we have left, we'll just do some review for the final exam. The last 2 homework sets will be due on Monday at 6 p.m. These 2 homework sets are on chapters 12 and 13, but they're very similar to one another, and I hope that you can recognize their similarities because we're calculating values at non-standard conditions. So homework due on Monday, all late homework. So remember, any homework set not submitted, so we're like past due dates, right? Any homework set can be submitted late for up to 50% of its original points. So any homework set, even if it's late, if you submit it complete, you'll get 50% of those points. So the last day I will accept those will be Tuesday, 4/23 at midnight, so that's reading day. So do not leave any assignment unsubmitted because that will turn into a 0. It is in your best interest to submit as many points as possible for online homework because it is such a large part of your grade. Okay, and then finally, so that's kind of the rolling due dates that are coming up here. The final exam stuff is all posted. So on Friday, I posted all of those final exam resources for you. There's, I think, 1 practice final exam and then just like a hodgepodge of chapters 12 and 13 questions. So it's not necessarily like an exam, but they're exam-like questions. So remember, our final exam is cumulative, and I'm just going to say that all chapters are represented equally. Because if you ask different people, they'll think different things. So we'll say all chapters 1 through 13 are represented equally. I believe chapters 12 and 13, I think, have like 18 questions to them or something like that, maybe. And then the rest is equal. All right, and then so that's the final exam. That all the resources are posted for you, including everything from previous midterms are present there as well. And so I linked everything in this mega page of resources. And then finally, I'll do a final exam review session on Tuesday, reading day, so a week from today, at 2 p.m. And then I think our final is the next day at 2 p.m. All right, but at least you get it over with early on, right? Okay, all right, so let's continue. Oh, and last thing, where's the wood block? Where did it go? Okay, yeah, so there's this wood block making its way around the classroom. So yeah, pass it along. So this wood block, it has become a yearly tradition of mine, or a semesterly tradition of mine, where I have students sign scrap piece of wood from my garage for them to sign. So now I have, I purchased a wood router, so now it has engraved 1250 on it forever. So you all can sign it and leave a part of yourself with me before you move on to the next phase of your engineering career and chemistry. And remember the fun times, the type 2 fun that we had in this classroom. So the reason for the piece of wood, if you're wondering, is because I don't know if you've ever noticed, I always bring my trusty block of wood to class every day, and it's to elevate my iPad, because I like to be ergonomic, but I'm cheap. I'm not going to go buy something to do what a piece of scrap wood can do for me for free. So one year, you know, students were asking about the block wood, and they really loved the block wood. They thought it was iconic, and so they're like, can we sign it at the end of the year? And I was like, oh, that's such a great idea. If you make it, yeah, well, you can sign it. But the thing is I like my scrap piece of wood, so I just grabbed another piece of wood from my scrap pile for everyone to sign. So it's cool is that they link together. So I have about 10 of them in my office, all stacked up of all the different years of students signing it. So if you could leave a piece of yourself with me, that would be great. I'll have it, the block piece of wood at on Tuesdays or Thursday's lecture, at the review sessions, at the final. So anytime you see me, I should have that block of wood where you can sign. And then if you ever come visit me one day, you can find your name. And then hopefully I'll have enough of those pieces of wood to build myself a new office, because my office is pretty rank. Okay, all right, so let's get started. We left off in chemical equilibrium. We looked at acids, bases, relating pHs to H+ concentrations. So remember, pH is just, P is a function, it means negative log of something. So it tells us how acidic or basic a solution is. I call this the magic square, where as long as you know one of the corners of the square, you know all of it. H+ concentration is related to pH by negative log. H+ and OH- are related to Kw, 1 times 10 to the negative 14. And finally, the one that most people know is that pH plus POH add up to 14. So all of these relationships are related to one another by these different quantities that we define at 25 degrees Celsius. And so we can calculate the pH of different solutions based upon the identity. We already looked at strong acids and strong bases, where we make the assumption that whatever the concentration of the strong acid is the concentration of H+ or hydroxide that we use our pH calculation from. So that's where we left off. These fully dissociate into H+ or OH- because they're strong electrolytes. But what we're going to come up with now are weak acids and weak bases. These have Ka and Kb values, so they have equilibrium constants. They only dissociate partially, so we actually have to use an ICE table to calculate how much H+ or how much OH- is present to determine the pH. But don't worry, it's a fairly straightforward calculation. We can use an approximation to do it. Okay, so let's do that right now. All right, so let's do a ICE table calculation involving a weak acid. All right, so a weak acid partially dissociates. It has a Ka value, and I give it to you right here. And so like all K values, equilibrium constants, it's equal. That value is equal to the ratio of concentrations of products over reactants. And so for a Ka expression, we want to write this acid acting like an acid. So when HF, which is a weak acid, acts like an acid, it pops off one of its protons, so this is what makes it acidic, but what's left behind is the anion, F-. So this is the Ka expression of HF acting like an acid. So the Ka reaction has an expression, products over reactants, and it's equal to this value. Right? So this is just like any other K expression that we've looked at before prior to this chapter. So I want you to calculate what is the pH of a 0.1 molarity HF solution. These are actually the easiest ICE tables you will ever work with, because everything is a 1-to-1 ratio. So how we approach this is recognize HF is an acid. So when we put that into water, our pH should be acidic, All right? So make sure when you express an answer that it matches what our intuition says. So since HF is an acid, we write HF acting as an acid. HF pops off an H plus and leaves an F minus. So we're going to use this equation for our ice table, where ice stands for what? What's I? Initial. C is change. E is equilibrium. So in order to calculate the pH, if I know my H plus concentration at equilibrium, I can figure out what my pH is. All right? So what we're going to say is that this concentration that's written on the bottle, 0.1 molarity HF, this is my initial concentration of HF. So that 0.1 molarity goes right there under the reactant. And so that means there's 0 of my products, nothing. So I just have 0.1 molarity HF, the intact one, the reactant, present right now. And I'm going to tell you, this is the easiest ice table that you'll ever do. So which way does the reaction have to go? Forward. So minus X, plus X, plus X. Then at equilibrium, that means we have a 0.1 minus X amount of HF, but X amount of H plus, and X amount of F minus. And then what's the trick with ice tables? E line goes into Ka, or the K expression. In this case, it's Ka. All right, and so I already have the expression for you. So both of those X's go on the numerator. So X squared over 0.1 minus X equals 6.6 times 10 to the negative 4. So right now, this requires the quadratic formula because there's this minus X in the denominator. But what did we learn here? Do we always have to use the quadratic formula? No, sometimes we can make an approximation. Think about, does this approximation work? It does, and the reason is because K is a really small number. So does this reaction go forward that much? No. So what kind of number is X? A big number or a small number? Small number. So if I can go ahead and just ignore that minus X, because that minus X is going to be a real small number. And 0.1 is actually a pretty big number. So if I take a big number and subtract a small number, that big number isn't going to change that much. So yeah, let's just say minus X is a very small number. All right, and so at this point, X squared over 0.1 equals a number. This does not require the quadratic at all. It's just a straightforward square root. So when you solve for X, you get 0.0081. And we were right, X is a very, very small number. Okay, so we're really good at calculating X. But what does X mean? What is X? It's the concentration of what? We solve for X, whoopee, we can put it in our calculator, but now we got to give that X meaning. What is that X? Look at your ice table. What did we assign X as? The concentration of the products. Yeah, any one of them. Which one is the best for us, probably? It is the concentration of H plus. Why do I want that? Because if you take the negative log, isn't that the pH? Yeah. So here we see that X is equal to the concentration of H plus because that's what we assigned it as in the ice table. And so now that we have that concentration, we can get that the pH of this solution is negative log 0.00811 or whatever. And then, yeah, you get a pH of 2.09. And so, yeah, we get a pH, it's acidic. Does that intuitively make sense? What did we put into water? An acid. Good. Yeah, and so you should get a pH that is acidic. So I told you this ice table is no different than other ice tables we did prior. We're allowed to do actually we're always allowed to do an approximation. They're honestly easier than any other ice table we've done prior because everything's a 1-to-1 ratio. There we go. Okay, so that is a ice table for a weak acid. Now we can do it for a weak base. It's the same idea. Bases, they produce hydroxide in water. So we want to write an expression, a Kb expression of a base acting as a base. So ammonia is the most common base that we interact with. So ammonia doesn't really look like a base. Bases typically, we think they have like a hydroxide attached to them, like lithium hydroxide, sodium hydroxide, calcium hydroxide. Those are all bases and kind of obvious because they have hydroxide literally attached to them. But here, ammonia doesn't quite look like a base because it just looks different, it's NH3. But this is one of our weak bases that we talk about. So why ammonia is a base is because when we put this base into water, both these have to be present in this equation, the ammonia and the water. What happens is that the lone pair on nitrogen takes one of the water molecule, the hydrogens on the water molecule, and dumps all the electrons on the oxygen. And so what you have is that ammonia gains a proton, and then we're left with a hydroxide as a product. And so since ammonia produces hydroxide in water, that's what makes it a base. Hydroxide is base. That's why it's a weak base. It makes hydroxide in water. And so in this case, calculating the pH of a base solution is very similar, except instead we're going to use a Kb expression instead of a Ka expression, where B stands for base. But the process is the exact same. We still want to do an ice table, right? Ammonia has a 0.3 molarity concentration. So I want to put that in the I line for ammonia. All right? Do I care about what the concentration of water is? I don't, because it's a liquid and it doesn't show up in the Kb expression. Only things that are aqueous show up in the in any K expression. So we don't really care about water. Okay, so which way does this reaction have to go? Forward. So minus x plus x plus x. Does this look familiar? I hope it does. So at equilibrium, we have 0.3 minus x of ammonia, the base, the original base, x amount of ammonium, and x amount of hydroxide. Just like before, we always put the E line into the K expression. So we get the expression, putting all of those variables from the E line in. We get x squared over 0.3 minus x equals 1.8 times 10 to the negative 5. Do you want to do the quadratic formula? No. No. Just make an approximation and say that minus x is going to be a real small number because k is really small. And so you can approximate this and get basically the correct answer within like the third sig fig. And again, so we're saying that this is very, very small. Okay, and now it just, we simplify it and it just becomes like a square root, a square rooted value. And so when you solve for x, you get something like 0.0023, and we were right, x is a really small number. It's barely going to change the value of that denominator if we left it there. All right, okay, we solve for x, yippee, but what does x mean? It's the concentration of what? Of the products. Yeah, very good, because the ice table, we defined that as x. So is it the concentration of H plus like it was in the last one? No, in this one, x is actually equal to the concentration of hydroxide. Notice how hydroxide right here is what we give the variable of x. So if we take the negative log of this number, do we get pH directly? We don't. We actually get POH first. So do recognize that when we use a Kb expression, we do x squared over initial concentration with the approximation. Here, since we're using Kb, we get hydroxide concentration. So when we negative log this, we actually get POH. POH equals, do I have it down here, is 2.63. Also think about it this way. Pretend you thought this was the pH, 2.63. 2.63 is what kind of pH? Acidic, but what did you put in water? A base. So does that work? No, that should not work in your head. So the last step is, okay, let's convert this POH into pH, right? And so let's remember the relationship pH plus POH equals 14, and so that means the pH is equal 11.37, and so that pH is in the basic regime, so now my brain is happy. All right. So those are the last two ice table calculations, this time for acids and bases. Really, it's the easiest type of ice table that you'll ever encounter because it always uses an approximation. But recognizing when you calculate X, are you calculating H plus concentration? You do when you're using Ka for a weak acid, where Ka, A stands for acid. Kb, on the other hand, you're given if I give you a weak base. B stands for base. When you solve for X, it's not H plus concentration, it's actually hydroxide concentration due to the ice table. So really doing any of these pH calculations really doesn't require doing the ice table as long as you know the process that's there, because it's always the same. If I give you an initial concentration of acid or base and I give you a K value, it's always X squared over initial concentration equals that K value. All right, okay, so those are acids and bases. So now let's talk about free energy and chemical equilibria. So remember earlier in the chapter when I said, okay, you have a chemical equilibria and you add a reactant and you disrupt the equilibrium, right? You add a reactant. Which way does the reaction shift if I add reactant? It shifts forward. Why does it shift forward? It has to do with free energy. So if the reaction shifts forward, it happens spontaneously. So the sign of delta G should be a negative value. If we relate to chapter, I guess, 10 material, right? Delta G should be negative. So this is where everything kind of comes together of, okay, when we do Le Chatelier's principle, when we say, oh, shifts left or shifts right, shifts to the forward, shifts backwards, why do those shifts happen? It's because the sign of delta G changes based upon the conditions that you produce, right? So we're going to look at three different equations here. We're going to relate free energy to equilibrium constant. So just like this equilibrium constant that we are looking at, depending on how much product and how much reactant is present at equilibrium, changes the value of delta G. If you have a really, really large K value and you make a lot of products, delta G is going to be a very negative number because you favor making products. The forward reaction is favored. So all of these things relate to one another. We'll talk about free energy at non-standard conditions and then free energy at different temperatures and how we can't use table values. And then remember, standard conditions with those little knots means 1 molarity or 1 ATM of everything, and the temperature is 298. Okay. So let's pretend we are at standard conditions. We have 1 molarity of everything. So let's say we have like this reaction, all right? This reaction, nitrogen, hydrogen goes to ammonia. If we have 1 molarity of everything at these certain conditions, if we were to go ahead and calculate what is Q when everything is 1 molarity, it's ammonia concentration squared over nitrogen concentration times hydrogen concentration cubed. So if everything is 1 molarity, it's 1 squared over 1 cubed. So Q is 1. Q is 1 at standard conditions. So this is how the table works, is like all those thermodynamic values, right? We start a reaction at standard conditions, so 1 molarity of everything. And then we ask ourselves, how does the reaction have to shift itself to get to equilibrium? Because technically, standard conditions, 1 molarity of everything, Q equals 1, may not technically be equilibrium conditions. But the delta G value we look at the table relates to how does a reaction have to adjust itself to go from standard conditions to equilibrium conditions. So what we see here is if we start at 1, but let's say for this reaction K is 9, which way does the reaction have to shift? If we start at Q equals 1 and K equals 9, we have to go what, forward or backwards? Forward. We got to make more product. So if the reaction spontaneously moves forward, what is the sign of delta G? Negative. Yeah, forward. If the forward reaction is spontaneous, delta G is negative. And that's exactly what the trend is here when we use this equation. When K is a big number times a negative, delta G is negative. So we see here large Ks typically have negative delta G values. The forward reaction is spontaneous. Versus small K values, if we start at Q equals 1 and we need to move backwards to make a small K value, make more reactants, delta G is going to be a positive number because the reverse reaction is spontaneous. So those delta G values that you looked up in the tables relate to the magnitude of K values that we can look up for that same chemical reaction, right? Okay, which way does it has to go? It has to go this way. Yes, yes, forward. So delta G is negative, so forward. All right, so that's one equation that we'll use, and then other equations we'll use is, okay, if we're not at standard conditions, if we're not at equilibrium conditions, what equation do we use? And that's this delta G without the not equation, where, okay, if we're not at standard conditions, we could have any value of Q. We can compare, okay, which way is spontaneous based upon the magnitude of Q and K. We've done this before, where we've compared, okay, if Q is bigger than K, I have too much products. So the reaction has to move backwards. So that means delta G has to be a positive number. So all of these things, these concepts are coming together, but now this is the mathematical proof why this happens. Maybe before you just had blind trust in me that if Q was bigger than K, the reaction went backwards. But no, it's actually the the second law of thermodynamics says that when Q is bigger than K, delta G is positive, so the reaction goes in reverse. So let's look at some examples in a minute of utilizing these three equations. Okay, so let's think about this. Let's go back to the earlier parts of this chapter where we just used Le Chatelier's principle. Remember Le Chatelier, the quick and dirty way to do it is you just say whatever you add due to the reaction does the opposite to undo what you just did. So let's add hydrogen to these reactions and predict what happens. So when we add, what are we doing? We're adding hydrogen. What does Le Chatelier say? When we add hydrogen to the first reaction, it moves forward. Perfect. What about the second reaction? We add hydrogen, it moves backwards. Perfect. All right, that was early in the chapter. That was the easy stuff. Now let's use the mathematical proof of why this happens. Let's think about it in terms of Q and K. So remember, Q is equal to the ratio of products over reactants. So if we add H+, we're increasing the concentration of reactants. So at this moment, Q is what? Greater than or less than K the moment we add a bunch of reactant. It's actually less than K. All right? Versus we add hydrogen to the second reaction, it's a product. So we're making the concentration of our product larger, where the products are in the numerator. So we see at this moment when we add product, Q is actually greater than K. All right? And so all of this is consistent with what Le Chatelier's principle predicted. When Q is less than K, there's not enough product, so the reaction has to move forward. When Q is greater than K, there's too much product, so the reaction has to go in reverse. But now we can relate this to the value of delta G. When delta G is negative, the forward reaction is spontaneous. But when delta G is positive, sometimes we think, oh, the forward reaction is not spontaneous, but that means the reverse reaction is spontaneous. Because of Hess's law, we can flip things. So here, if the forward reaction is spontaneous, in this moment, delta G should be a negative number because the forward direction is spontaneous. Le Chatelier's principle says the reaction automatically pushes towards the forward direction. Versus when Q is greater than K, the reverse direction is spontaneous. So what we'll see is that delta G is actually a positive value here. Okay, and so where am I getting these delta G's? I'm getting it from this equation. Delta G equals delta G naught plus RT ln Q. If I actually calculated a value of Q, if I actually had a value of delta G naught and actually plugged in those values of the Q conditions versus the K conditions, I would get delta G values without the naught that predict exactly what Le Chatelier says as well. Okay? When the forward direction is spontaneous, delta G is negative, but when the reverse direction is spontaneous, delta G is positive. Okay, so let's look at an example. All right, so let's, so notice I have two different equations here, delta G naught equals RT ln K, and then another delta G equation, but it involves Q. So make sure you recognize when do we use which equation. The variables give it away. So here I tell you that the KSP, or the solubility product of calcium hydroxide, is this number, 10 times 10 to the negative 6. And then here is the KSP expression, right? KSP 4.8 times 10 to the negative 6. So what is delta G naught for this saturated solution at 25 degrees Celsius? So which equation should I use, the first one or the second one? Yes, probably the first one. Why? Because it has a K in it, and I give you a K, and I'm asking you to calculate delta G naught. So simply, this is plug and chug. Let's use delta G naught equals negative RT ln K. R is the 8.314 joule mole Kelvin. Temperature is 298. And then ln K, so in this case it's KSP, but whatever. Ln 4.8 times 10 to the negative 6, right? And so when you put all these numbers together, you will get a joule per mole value because that's the unit of R. But do remember, sometimes it's easier to write things in kilojoules per mole. So this is 30.4 times 10 to the 3 joule per mole, or you can call this 30.4 kilojoules per mole, same thing. All right. What do we notice here? Delta G is a positive number, so is this reaction spontaneous in the forward direction? No, it's not, because it's a positive number. Look at the value of K. K is a really small number. So does this reaction make a lot of products? No, its name stays mainly on the reactant side. So all of that hopefully should make sense here, in that K is really, really small. Delta G is really, really large, really positive, sorry, because this is not a spontaneous reaction. Okay, all right, so pretend we have a saturated solution of calcium hydroxide at equilibrium. What is true? If we're at equilibrium, does KSP equal 0? No, KSP is a constant and never changes at that temperature. Does Q equal 0? No, but what does equal 0? Oh, I guess nothing equals 0. Here, Q equals KSP, where Q is what our actual measured conditions are. KSP is at equilibrium. The giveaway here is we're saying we're at equilibrium. So that means our concentrations are at equilibrium. KSP means at equilibrium. Okay, all right, so pretend we're still at equilibrium. And we want to add some calcium 2+. So it sounds like we're disrupting the equilibrium. So the moment we add calcium 2+, are we at equilibrium anymore? No. So we have to think, how does the reaction have to shift to get back to equilibrium? All right? So recognize when is Q used, when is K used, and the difference there. So the moment we add calcium 2+, the only thing that changes is K. Q. K is a constant. How do I know that? What do we call big K? Equilibrium constant. It's a constant. The reaction will always tend to gravitate back to that ratio of products over reactants, whatever value that is. Q is just the concentrations we have at that moment to allow us to predict how does the reaction have to shift to get back to equilibrium. So the moment we add calcium 2+, we're essentially disrupting it. Disrupting this reaction, we only change Q. And so at this moment, when we disrupt this equilibrium, all we're doing is changing delta G as well, because delta G naught is a table value. It's a table value. This table value is related to K, which is an equilibrium constant, versus delta G. This equation, delta G equals delta G naught plus RT ln Q. This delta G equation does depend on what concentrations are actually there. And so the idea here is, when does delta G equal 0? It's when we're at equilibrium. Hopefully this sounds familiar from chapter 10. When we're already at equilibrium, delta G is equal to 0, or this is where Q equals the KSP that's given for the reaction. Okay, so let's actually do a calculation. All right. So here's the same information. There's the KSP for calcium hydroxide. There's the delta G value. So we want to predict. We make a solution that has these concentrations. So calcium, it says calcium plus. This should be calcium 2 plus, but whatever, doesn't change anything. Is that concentration, and hydroxide is this concentration. And I'm going to ask, does a precipitate form? So let's go about this question. So from the balanced chemical equation, we should be able to get that the KSP expression is products over reactants. I give you a KSP value. It's times 10 to the negative 6. But the KSP expression is the product, so calcium 2 plus concentration times hydroxide concentration squared. These two things, I literally just gave you the concentrations. So I can go ahead and calculate Q. Just shove in those concentrations that I gave you into the KSP expression. So 0.005 molarity times 0.05 squared. And so if you calculate that, we get that Q is 0.05 times 0.05 squared. We get that Q is equal to, I'm just going to estimate 1 times 10 to the negative 5. Compare this number. This is Q. We just calculated. This is Q. Compare this to K. K for this reaction is 1 times 10 to the negative 6. So which one's bigger? Q. So what does that mean? You, at this moment, when you mix all this junk together, you have too much what? Products. So look at the reaction. If you have too much product, which way does the reaction shift? Reverse. So what should your eyeballs see? Solids should come out, right? If the reaction goes in reverse, Q is bigger than K, a solid should come out. How do we know that? Look at the reaction. With your eyeballs, pretend that this reaction goes in reverse. If it goes in reverse, we make a solid. So here, when Q is greater than K, a precipitate forms. I don't like to memorize, oh, if Q is bigger than K, a precipitate forms. No, I just look at the reaction, and I think to myself, okay, if Q is big, I have too much product, so I need to go backwards. So going backwards forms a precipitate, right? So if the reaction goes backwards, what should the sign of delta G be? Positive. So let's check it for ourselves. So in this case, because we have Q conditions, what we want to do is actually use the second delta G equation. Because we're not at standard conditions. We're at just some random conditions that I want to predict does the reaction go forward or backwards. So I'm going to put together those Q values in that delta G to predict whether the reaction moves backwards or forward. So delta G equals delta G naught. I already gave it to you. 3.4 times 10 to the 3 joules per mole, plus R, so 8.314, temperature 298, and then ln Q that we just got, ln 1 times 10 to the negative 5. I approximated, but the answer should still be right. And so what we get here is that, yes, delta G is positive, like 2.4 kilojoules, right? So it's a very large positive number. And so, yes, we do get a positive delta G come out, indicating that this reaction has to move in reverse. All right, last one here. It's the same idea, but just different concentrations. I want you to calculate Q and tell me, does a precipitate form? So Q here is going to be equal to calcium concentration times hydroxide concentration, but squared. I know it's squared because there's a 2 coefficient in that chemical equilibrium. So I'm just going to plug in those values, 0.001 times 0.01, but it's squared. And so we get that Q is equal to squared. Q is equal to 1 times 10 to the negative 7. So compare that to K, which is 1 times 10 to the negative 6. Does a precipitate form? It does not, because K is bigger than Q. So I like to think here, okay, if Q is if too small of a number, I don't have enough products to move backwards. That's how I like to think of it. So here, when K is bigger than Q, no precipitate forms. All right, and so if no precipitate forms, delta G is actually going to be a negative number, because that negative number keeps the reaction spontaneous in the forward direction, preventing it from going in the reverse direction. So our eyeballs will see a solid form. But let's prove it to ourselves, where we use the exact same equation. Delta G equals delta G naught, that's given, so 3.4 times 10 to the 3 joules per mole, plus R, so 8.314, times the temperature given, 298, times natural log of this Q, which is 1 times 10 to the negative 7. And so when you get this, yeah, you get a delta G that's a negative number, meaning that just the forward direction is spontaneous, not the reverse direction is spontaneous. All right, so we'll keep seeing everything dissolved. We're going to stay on the product side here. Everything's going to stay dissolved. You're not going to see any solid being formed at all here. All right. So I want us to think about, okay, us predicting the way reactions shift. You know, when we compare Q and K, I feel like understanding, okay, too much product, not enough product is a good way to predict shift. But really, thermodynamically, if you want the real reason why these things shift, okay, not the quick and dirty way, it's actually the second law of thermodynamics that we're looking at here. Delta G, Gibbs free energy, proves to us that the reaction shift forward and in reverse, and is consistent to even the quick and dirty way we were doing it before. Okay, so we have 2 more questions here, and we're good. All right, so let's put everything together. All right, so we looked at delta G without the naught, so at non-standard conditions. So let's look at other ways we can use delta G without the naught, meaning at different temperatures. Okay, so we've done this before. We've calculated delta G at different temperatures where we've assumed delta H and delta S stay constant with temperature. Stay constant. We've done this before. All right? So what I want to do here is let's add the element of chemical equilibrium. So I want you to calculate what is Kp for this reaction at equilibrium when we're at 25 degrees Celsius. So obviously I need to, since I want to calculate K, I need to use the only equation that has a K in it, and that's the first one. Right? The first one has a K in it. But now the question is, am I allowed to just use the table values of delta G for this question? When are table values good? At standard conditions, which is 1 molarity, 1 ATM of everything, but also at what temperature? 298. So, given this question, am I allowed to just use the table value of delta G? Yes, I am, because what temperature are we at? 298. And did I give you the table value of delta G of this reaction? Yes, I did. So we can just go ahead and use this delta G value, because remember, that naught means at standard conditions. So we can just simply use delta G naught equals negative RT ln K, where temperature equals the 298. This delta G is the 43.2 kilojoules per mole, but let's actually do it. That's stupid. Junk mail. Put in those numbers here. So the idea here is that we are at standard conditions. So we are absolutely allowed to use those table values. Standard conditions. All right. So the work here, delta G, remember, needs to be in joules. So positive 43.2 times 10 to the 3 joules per mole equals negative R, 8.314 joules per mole Kelvin, temperature 298 times natural log K. So, or Kp in this case. So we are solving for the equilibrium constant of this reaction. And what's kind of cool is that this reaction, its equilibrium constant is actually the partial pressure of CO2 that's present based upon the equilibrium that's here. The only gas is CO2. Everything else is a solid. So that's kind of cool. And so when you solve for that, yep, you get a Kp of really, really small. All right? So if you have a sample of lead carbonate in equilibrium with lead oxide, you're going to measure a very, very tiny amount of CO2 present in that container at 25 degrees Celsius. So at like regular room temperature. But now let's change it. So we were at standard conditions, so we were allowed to use the table value. But now, are we at standard conditions? We are not. We are at 200 degrees Celsius. So are we allowed to use this delta G value? We are not. We cannot use that value because, again, that one is only good at 25 degrees Celsius. But what we can do instead, and we've done this before, is let's calculate delta G at a different temperature using delta H and delta S, because we're going to assume that these stay constant with temperature. These are constant, so let's calculate what is the new delta G at this elevated temperature, so 473 Kelvin, and use those delta S and delta H values to achieve that. So essentially, we have to use both of these equations. We're going to use the second equation first to calculate delta G, then use the first equation to use that delta G to calculate K. So we're going to use both of these equations at these non-standard temperature conditions. So, all right, I'm going to use that second equation first, delta G equals delta H minus T delta S. This allows me to calculate delta G at that elevated temperature. So delta G equals, at this elevated temperature, equals delta H. So again, make sure these units match. 88.3 times 10 to the 3 minus the temperature we're at, so 473 Kelvin, times Gibbs free energy, 151.3 joule Kelvin. And so what we get is that this new delta G value at elevated temperatures is 16.7 times 10 to the 3 joules per mole. All right? So what we see here is that at this elevated temperature, the reaction still isn't super spontaneous in the forward direction, but it's more negative than it was at standard conditions. So when we heat this thing up, we actually make the reaction a little bit more spontaneous. This isn't our answer. The question is asking, it's not asking what is delta G at this temperature. Right now, this would just simply be a chapter 10 question. If I just asked you, what is delta G at this elevated temperature? No, now we're adding the element that, oh, delta G has a relationship to its equilibrium constant. So now I'm going to use the answer I just got and shove it into delta G equals negative RT ln K. All right, so I'm going to put that new delta G value, so 16.7 times 10 to the 3 joule per mole equals negative R, so 8.314, times this new elevated temperature, 473, times ln K. So solve for K, and I think you get at this elevated temperature, the pressure of CO2 that's present is actually a lot higher at higher temperatures. Right? It would make sense if this reaction is endothermic, that heating the reaction pushes the reaction in the forward direction. And the reason is that heating this reaction up makes delta G more negative and then pushes that reaction forward. So K becomes a larger number and we have more CO2 at equilibrium. So this slide is very much like a previous slide we did in chapter 10. It's just we added this element of relating Gibbs free energy to K, equilibrium constant. So the big idea is when K is a large number, you need to make lots of product. So delta G is typically a negative number, versus when K is a small number, delta G is a positive number because the forward direction is not very spontaneous. And that's the big takeaway from relating equilibrium constant and Gibbs free energy from earlier chapters. Le Chatelier's principle isn't just like a, back of the envelope estimation or anything. No, it's just an estimation that completely agrees with the second law of thermodynamics mathematically. All right, now I think that's cool. I like when the math matches everything else. Okay, so that means part 3 for this chapter 12 homework is due on Monday. It's acids and base calculations and free energy calculations. But I kind of like that I went out of order with these chapters, because what we're going to do is now go back to electrochemistry, I'm sorry. But I want you to see the similarities here. We just calculated delta G at non-standard conditions. Remember when we talked about cell potentials and we did cathode minus anode, the table values? When did I say those were good at? Table values. They're only good at standard conditions. So we are actually going to calculate cell potentials at non-standard conditions. And what you're going to see here is that the two equations, they are exactly the same. If you squint your eyes, they are twins to one another, of calculating Gibbs free energy at non-standard conditions and calculating cell potentials at non-standard conditions. All right? So recall that we talked about galvanic cells for a long time. We were always looking to make positive cell potentials, because I just told you and I made you memorize that positive cell potentials were spontaneous. And in the world, when we think about spontaneous reactions, that's what we want to strive for. So we always searched for how do I set up my electrochemical cell so the cell potentials are spontaneous. So the question is here, well, why are those positive cell potentials spontaneous? Why are those ones the spontaneous galvanic cells? It actually has to do with our friend Gibbs free energy. So the last kind of expression that we're going to use here is what relates free energy to cell potential. And so what we see here is that the free energy for a reaction is related to the negative N. So N, remember, N is the number of electrons transferred in that redox event. F is Faraday's constant, which we talked about earlier in electrolysis, times E. So you see, when E is a big positive number, delta G is a negative number. But when E is a negative number, it's non-spontaneous, delta G is a positive number. And so we see here is that it all agrees with everything we've talked about before, that when delta E is spontaneous positive, delta G is negative. And we have proof here via this equation. So everything comes together now, right? At the end of 1250, and all of these ideas come together. Gibbs free energy from the second law of thermo, chemical equilibrium from last chapter, and cell potential from this chapter. All three of these are related to one another via delta G. Here, delta G and E are related from by this negative sign. From chapter 12, we said that delta G was related to K. Its magnitude and sign changed based upon if K was big or small. And then finally, we will talk about free energy, or sorry, chemical equilibrium and cell potential. What we'll see here is that in order for a battery to be useful to us, we don't want our batteries at equilibrium. Once our battery is at equilibrium, it's dead. Because what is equilibrium? It's the forward and reverse rate are equal to one another. So if you think about like, I don't know, like riding an electron wave to like power some device, we don't want equilibrium because that's no net effect. We want to be able to ride a high to a low voltage, so we want our chemical cell to be not at equilibrium conditions in order to harness the energy there. All right, so just to kind of reiterate standard conditions versus non-standard conditions, just like we talked about with delta G. When I put the little naught here, E naught, delta G naught, delta H naught, all that, that's deliberate. I'm not making a mistake. Versus when I don't include the naught, again, I'm not making a mistake. The naughts mean at standard conditions, so it's A-okay to use the textbook values. Products minus reactants, cathode minus anode, whatever, right? You're good to use the naught there. If you're at standard conditions, meaning 1 molarity of everything, 298. But when we're at non-standard conditions, and these are most typical of our cell, like our batteries that we use, they're not going to be built at 1 molarity. We use different terminologies. Notice that there are no knots here. E, delta G, and Q. All of these are related because they're not at standard conditions. And again, I'm deliberately leaving the not out. It's not just a mistake of mine. I'm trying to indicate these are at non-standard conditions. So you want to use these versions of delta G, the delta G that includes Q, or what we're going to learn here, this is our Nernst equation, where if you look very closely and squint your eyes, This E equation, the Nernst equation, is very similar to the delta G equation I just introduced. Squint your eyes. Don't they look exactly the same? They both have this factor of natural log or log of Q. Basically, we're taking, okay, these are the textbook values, but these are the values I actually have in my beaker. So let's take the textbook value and incorporate what the concentrations I actually have to tell the reader or determine what is the measured cell potential that I'll actually read at these conditions. And that's what the Nernst equation does. All right, so why is this important? It's important because batteries, they don't stay the same voltage all the time. That's one way you know your battery is dying. If, like, you turn on your car battery and you turn off all the electronics and whatever, and you take a multimeter and you measure the voltage drop between the terminals. If you're reading something less than like 14.5 volts or something like that, then it's probably a bad battery. Or I don't know what the idle is. Maybe 13.8, I'm not sure, I forget. But if you have a very low voltage drop, a very low potential, that means that you're not getting as much electrochemical cell potential than you should, probably because your concentrations are all out of whack. So let's look at this example of a spontaneous cell working over time and how concentrations change, therefore the voltages change over time. So here's my example. Zinc solid going to zinc 2 plus, copper 2 plus going to copper 0. So I'm just going to tell you that copper 2 plus is the what? Copper 2 plus is the anode. Is that right? No, it's the cathode. Yes, it's the cathode. And then zinc is my anode. Right? So here are my two reduction potentials. And so when I do cathode minus anode, I do 0.34 minus negative 0.76. So I get a positive cell potential of 1.2. Fantastic. So it's positive, it's spontaneous, great. So I will measure a cell potential of 1.2 only if my copper concentration is 1 molarity and my zinc concentration is 1 molarity, okay? If I set it up so everything's 1 molarity and I put my electrodes in and I measure with my voltmeter or my multimeter, I will get 1.2 volts. But here's the thing. So at this moment when copper is 1 and zinc is 1, tell me, what is Q at standard conditions? Remember, Q is products over reactants. Just think of this reaction as an equilibrium. So Q is equal to zinc concentration plus, or over, sorry, copper concentration. So if we're at standard conditions, Q is equal to 1, yes. Hopefully that sounds familiar. We did the same thing with delta G. When we're at standard conditions, we are equal to delta G naught. Same thing here. When we're at standard conditions, we will measure an E cell naught. Okay, but here's the thing, a reaction's happening. A reaction's happening, we're going from reactants to products. So over time, as the cell is running, right, our little Energizer bunny is going. How does the mass of zinc change over time? Zinc solid is a what in this reaction? Reactant. So it's going to be consumed. Think about a BCA table. You don't have to do the whole thing. If you do a BCA table, this reaction is moving forward. So it's minus x plus x plus x. So zinc mass will what over time? Decrease because it's a reactant. But then the copper solid mass is going to what? Increase, yeah, spontaneously, right? So those are the masses of your electrodes changing. But what about the concentrations, okay? Because the ions are involved in the reaction as well. Copper concentration will what? Decrease. Zinc concentration's gonna increase because it's a product. So with that in mind, how does the value of Q change over time? You just told me that the concentrations change, that copper concentration decreases, zinc increases. So remember, Q is equal to zinc concentration over copper ion concentration. You just told me zinc goes up and then copper concentration goes down. So how does Q change? It increases. Do you agree? Yes, it agree. Right? And remember, Q generally is products over reactants, so as this reaction's moving forward, we're making more products, so it makes sense that Q is increasing. And so now the last question is, how does the measured cell potential change over time? Notice that I wrote the Nernst equation, probably because it's important, all right? So as Q increases, look and see where Q is in this equation. We have log Q right here, right? E naught doesn't change. That's the book value. So when we start this reaction at standard conditions, we're going to start at 1.2. But over time, as Q increases, as we increase the concentration of our products, log Q increases. So we subtract a bigger and bigger number over time. So how does that measured cell potential change? It goes down because log Q gets bigger. So we're subtracting a bigger number. So cell potential goes down. How do you think? Do you ever use one of those battery like tester things that tell you if it's like dead or not? How do you think they work? All they do is measure the cell potential, because a brand new, spanking new battery, like a Duracell battery, will measure I think like 1.8 volts. I think the manufacturer writes 1.5 or something, but it'll measure 1.8 when it's brand spanking new. But you let it in a, put it in your device for a long time, even before it's dead, if you just take it out after it's been used for a long time, you've accumulated more products. You've consumed your reactants, Q gets bigger. If you measure the voltage across an older battery, you're going to get a lower potential. So you can kind of check the newness of a battery by just measuring the potential for different ones. All right, I'm cheap, so oftentimes I have like a big box of batteries, and so I just need like a little battery to do this small little task, so I'll just go through and find like the one with the most juice in it to go and do my thing. And so that makes sense that as we use our batteries, cell potential goes down over time. You're not going to just get this free energy from whatever and the cell potential increase over time. It does go down until your cell potential is 0 and your battery is dead. Right? Okay, so let's talk about, we got 20 minutes. Okay, good. And then, oh, I forgot. I didn't think I'd get this far, so I didn't do the demo. I'll do the demo for tomorrow. So let's do a couple calculations of using that Nernst equation now. Here, I'm just showing you the relevance of the Nernst equation, how we use it, how cell potential does change over time because Q, our concentrations are changing over time. So how else can we utilize this equation? So here I have a big redox reaction. Let's calculate E cell at standard conditions, and I reinforce that this is at standard conditions. I say everything is 1 molarity. All right, so to calculate E cell, and I give you reduction potentials, am I allowed to just do cathode minus anode? Yes, because we are at standard conditions. So you just have to identify what is the cathode, what is the anode. So let's look at that balanced reaction. I know that there's a lot going on here, but remember, if one thing's the cathode, the other thing has to be the anode. So I'm going to do the easy one. I'm going to do iodine. I minus has an oxidation number of what? -1. I2 has an oxidation number of 0. So I is being oxidized. So I is probably the anode. So that makes the chromium thing the cathode. All right. So that means if we do cathode minus anode, so 1.33 minus 0.54, we get a cell potential of 0.79, right? Okay, perfect. So now, notice that we calculated the E cell at standard conditions. Everything was 1 molarity. I can tell at standard conditions because of that dot. Here, I'm asking you to calculate E cell without the dot. Is that a mistake? No, that is deliberate. I'm trying to show you that, hey, these are at non-standard conditions, so we have to use the Nernst equation. But the thing is that this Nernst equation still needs E cell naught. We still need this value, 0.79. We still need it. But we also need Q for this reaction to calculate the rest of this Nernst equation. And so that's probably the trickiest part, is to get Q. Remember, Q is just like K. It's products over reactants. I gave you the balanced chemical reaction, so we just need to put everything that has a concentration into the K expression. So Q is equal to concentration of chromium 3+, but it is squared. Do I put I2 solid in K or Q? No, you don't. Solids don't go in there. What about water? No. Okay, perfect. So chromium 3 plus is the only thing that goes in there. Next, we put in the dichromate, so Cr2O7, 2 minus. Just to the 1, so no power. H plus concentration, oof, to the 14th power. Dang. It's there. You got to follow the rules. You got to follow. Don't worry, it's going to go away. All right, so it's H plus to the 14th power, and then I minus to the 6th power. Yeah, you might be wondering, man, those are some crazy numbers. And you'll see why standard conditions are standard conditions. Because look, now let's plug in the numbers that the question actually gives us, and it's actually not that bad. All right, so I tell you that the dichromate concentration is 2 molarity. And I give you that the chromium 3 plus concentration is 1 times 10 to the negative 5 molarity, but that whole thing is squared. The H plus concentration is what? 1 molarity. So what is 1 to the 14th power? 1. See, that's why standard conditions is, standard conditions. Yeah, because we get some of these crazy exponents, but when it's 1, it's nice. Because same thing with I minus. If we make it 1 molarity to the 6th power, it does nothing. It just goes away. We can ignore it, right? And so what really matters here is the concentrations of those chromiums, right? So what these people did was like forced the pH of the compartments to be pH of 0. Right? Okay, so plug in that all those numbers and you get Q equals, oh, I have it right there, is 5 times 10 to the negative 11. All right, that's not our answer. We need to put that Q into the Nernst equation. So if you look closely, we're trying to calculate that measured cell potential given these concentration, non-standard concentrations. Compare it to standard conditions. Now we're just missing N, and I kind of skipped this part. We need to figure out how many electrons are being transferred in this reaction. I'm going to show you how to do it 2 ways. Okay, so the first way is look at the reduction half reactions. Notice that the first reaction requires 6 electrons and the second one requires 2 electrons. So if you had to flip one and add them together, what are the electrons, how many electrons are being canceled out in the background? 6, yes. So N is 6. Right? Here's another way to do it. Let's look at the full balanced chemical reaction. You told me that I minus has an oxidation number of -1, where I2 has an oxidation number of 0. So, but how many I minuses are here with a negative oxidation number? 6 of them. And so we're oxidizing it, so these things are losing 1 electron, but how many are losing 1 electron? 6 of them. And so that requires 6 electrons to do that entire process. So right here, this requires 6 electrons because there's 6 I minuses. And so that's another way you can check yourself to figure out how many electrons are involved in the process when it's not as obvious. You can kind of like half balance it to see what it needs to be. All right, so now we just plug everything in. Our measured cell potential is going to be what it normally is at standard conditions, minus 0.0592 volts over N, so 6 log this tiny number, 5 times 10 to the negative 11. And so what you get is at these concentrations, at slightly different concentrations of those chromiums, we actually get a cell potential that packs a bigger punch. We increase it almost a whole 1/10 of a volt, right, just by changing those concentrations via the Nernst equation. All right, let's do that same, oh no, different one. Okay, different one. Okay, let's calculate the cell potential for this cell, but here I'm presenting the information a little bit differently. I'm presenting it via line notation. So this can be tricky because in the previous question, I give you the full balanced chemical equation, I give you the half reactions, so it's quite easy to figure out what Q is because you just do products over reactants. But when it's in line notation, it's a little bit trickier, but I'll help you here, all right? So when we read line notation, we always read this as the anode on the left and then the cathode on the right, all right? So that means the anode is where your oxidation is occurring and your cathode is where your reduction is occurring. So we can put these things together and write that full balanced redox reaction right here, where copper is being oxidized, so it's going from copper 0 to copper 2+, and silver is being reduced. It's going from silver plus to silver 0, all right? So here with the balanced redox reaction, we can easily get the expression for Q, where it's products over reactants. So Q is equal to copper 2+ concentration over silver plus concentration, but it's squared. All right, this is important because we are using the Nernst equation because this electrochemical cell is not at standard conditions. I can tell because there are concentrations that are not 1 molarity. So those concentrations will show up in the Nernst equation. But there's a bigger strategy here. We need to use the Nernst equation. I need to get the regular cell potential at standard conditions. I need to get N, and I'm halfway to getting Q. So let's just go in order of all the things we need in the Nernst equation. Let's get the cell at standard conditions. So we simply have to do cathode minus anode. So note here that copper 2+ is our anode. Silver is our cathode. So I have those reduction potentials there. So the cell potential at standard conditions is simply 0.8 minus 0.34, where I identified copper as the anode, silver as the cathode. I still need this number for the Nernst equation. If we were at standard conditions, we would read a regular cell potential of 0.46 volts, but we're not at standard conditions. So this is where the Nernst equation comes into play. So next, we need to get N. So hopefully you can just look at this and tell me what is N, how many electrons are being transferred? 2. Yeah, you can also look at the half reactions. Copper requires 2, silver requires 1. So you'll have to double that silver reaction to get N equals 2. And now we just need Q. Q, put in the numbers that are actually given. I tell you that copper is 0.5 molarity. I tell you that silver concentration is 3 molarity. So just put those numbers in. So Q is equal to 0.5, and then silver is 3 molarity, but it is squared. And so we get that Q is equal to 0.0556. Okay, now we have everything we need to plug into the Nernst equation to calculate what is the actual measured cell potential that we'll get at these conditions. So let's do that. So cell equals the regular cell potential, so 0.46 minus 0.0592 over N, which is 2 log of that Q we just got, 0.0556, all right? And so we get that the cell potential is a little bit boosted. It's 0.497 volts at these concentrations. So we were able to up that cell potential a little bit by just playing with the concentrations a little bit. And the follow-up question was calculate delta G, I guess, maybe, I don't know. Maybe not, but since we have the cell potential, we could easily calculate delta G by using delta G equals negative NFE, where you plug in E, use Faraday's constant, and N of 2, and you get a negative value of delta G here that we get for this electrochemical cell. All right, let's just do one more, a little bit trickier, still using line notation, and then we'll stop there. And this is also a electrochemical cell at non-standard conditions, but it's special. It's kind of weird, and I should have brought a demo for it, but I'll bring it on Thursday. All right, so this electrochemical cell is weird because what substance is at my anode? Copper. But what substance is at my cathode? Copper. Weird. Is that weird? This is my anode. This is my cathode. Right? So this is called a concentration cell because the only thing that's different in this electrochemical cell is the concentrations on the anode and cathode side. They're both actually copper. So tell me, if I tell you that the copper reduction potential is 0.34, what is the standard reduction potential for this reaction, cathode minus anode? 0. Do I technically need to even give you this value? No, I don't. I don't have to give it to you, because recognizing your cathode and anode are identical, they're going to have the same reduction potential. It's going to be 0 volts. So what that means is when we set up a electrochemical cell at standard conditions, 1 molarity of everything, copper as your cathode and anode, you're not going to produce a potential. But here, are we at standard conditions? We are not. And what we're going to see is we will produce a potential because the concentrations are different. Even though the cell potential at standard conditions is 0, Q is non-zero, and we actually will produce a small voltage based upon what's happening here. So what's a little bit tricky with this, with line notation, I love line notation because it clearly shows you, here you have your anode, here you have your cathode, because we read electrons left to right. What's hard to get is the full balanced equation. So remember, at your anode, oxidation is happening. So the reaction that's happening is copper solid is turning into, it's losing 2 electrons and producing copper 2+. And in the anode compartment, I'm telling you that it's 0.1 molarity, and it's losing 2 electrons. So that's the anode reaction, the oxidation reaction. This is important because both of these are copper, and when I write Q, I don't know which one's on top. Is it 1 on top, or is it 0.1 on top? I don't know, so you have to write the reactions to prove it. So here, in the anode reaction, copper 2+ is a product. That's 0.1 molarity. So let's do the cathode reaction. The cathode reaction, copper 2+ is actually being reduced, where copper 2+ is starting as 1 molarity. You're adding 2 electrons, and you're making copper solid. So the full balanced reaction will add these 2 reactions up, but I hope you can recognize what will Q be. Q will be the copper 2+ that's in the anode over the copper 2+ that is in the cathode. Do you see how I got that? Because 2+, the copper anion, cation, is the product in the anode reaction, but it is the reactant in the cathode reaction. So I'm just simplifying it, saying, okay, Q is equal to the copper 2+ in the anode over the cathode. So therefore, the copper 2+ concentration is Q is equal to 0.1 over 1. So it is, I think, 0.1. That is Q. That's Q. And now we're just the Nernst equation away. Okay, so tell me what, so we got Q, there's Q, what is N? 2, and then E cell is 0. So we have everything we need to calculate the Nernst equation. So the cell potential we'll actually measure is 0 volts minus 0.0592 volts over 2 log of the Q we just got, so 0.1 whatever. All right, and so what we get is that the E cell, for just having a difference in concentration, is 0.0296 volts, so almost 30 millivolts we can produce just by having a difference in concentration across your 2 electrodes. So I'll show that demo on Thursday. We have a couple more slides to talk about. We'll talk about batteries. On Thursday, and the rest of the class will do a little bit of review. Where'd that piece of wood go? You have it down there? Okay, if anyone up there wants to sign the thing, you can come down here, come to office hours.